The experiment that questioned everything. Unveiling the quantum. 1. Look at your hand. It seems solid, continuous, and real. The chair you're sitting on feels firm beneath you. The world, to our senses, is a place of predictable certainties. We exist here, not there. An object can be in one place at one time and one place only. This is the classical world, the intuitive reality that has governed human thought for millennia. It's a comforting illusion, a simplified map we use to navigate a territory far more complex and mysterious than we could ever have imagined. For beneath this veneer of solid reality, at the infinitesimally small scale of atoms and particles, the universe operates on a set of rules so bizarre, so contrary to all logic, that they shatter our most fundamental assumptions of existence. There is one experiment, elegant in its simplicity and devastating in its implications, that serves as the perfect gateway into this bewildering realm. It is not an obscure footnote in physics, it is the very heart of the mystery. The legendary physicist Richard Feynman once claimed that this single experiment contains the central mystery of quantum mechanics, a puzzle that no one has ever truly solved. It is known as the double-slit experiment. And it does more than challenge our understanding of science. It forces us to question the very nature of reality itself. It is the moment humanity peeked behind the curtain and discovered that the universe is not a clockwork machine, but a shimmering, probabilistic ghost. To truly appreciate the profound weirdness of the quantum world, we must first solidify our understanding of the world we think we know. Let us begin with a classical, common-sense scenario. Imagine you have a large panel, like a piece of plywood, and you cut two narrow, parallel vertical slits into it. You place this panel a short distance in front of a solid backstop wall. Now, you stand back and begin to fire tiny marbles from a gun, aiming in the general direction of the slits. The marbles are particles, solid, discrete objects. Each marble that makes it through the panel must pass through either the left slit or the right slit. There is no other option. What pattern do you expect to see on the backstop wall? It's simple. You'll find two distinct vertical bands of impacts, which are rough outlines of the slits themselves. The marbles that went through the left slit form one band, and those that went through the right form the other. If you were to plot this as a probability distribution, you'd have two peaks, with the highest probability of a marble landing directly behind the center of each slit. This is intuitive. It's logical. It's the world of cause and effect we rely on every day. Now, let's switch our projectile. Instead of marbles, let's consider waves. Imagine our setup is now a large tank of water. The backstop is a wave detector, and instead of slits in a panel, we have a barrier with two small openings. At one end of the tank, we generate a continuous, steady wave. As the wavefront propagates across the water, it reaches the barrier. At this point, each opening acts as a new source of circular waves, which spread out on the other side. As these two new sets of waves travel towards the detector wall, they interfere with each other. This interference is key. Where the crest of one wave meets the crest of another, they combine to create a much larger wave. Constructive interference. Where the crest of one wave meets the trough of another, they cancel each other out, resulting in calm water. What pattern does the detector see? Not two simple bands. It records a series of multiple alternating bands of high and low intensity. The central band, directly between the two openings, is the strongest, with progressively weaker bands fading out to the sides. This is the classic, unmistakable signature of wave behavior. So, we have two clear, distinct outcomes. Particles produce a two-band pattern, and waves produce a multi-band interference pattern. The distinction is absolute. Now, let us hold this knowledge and prepare to enter the quantum realm, where such clear distinctions cease to exist. We return to our original setup with the two slits and the detector screen. This time, we will fire something much smaller than marbles: individual electrons, the fundamental particles that orbit the nucleus of every atom. An electron is a particle. It has a specific mass and a specific charge. It is a single, indivisible entity. Therefore, our classical intuition screams that the result must be the same. Each electron must pass through either the left slit or the right slit. The final pattern must be two bands. With great anticipation, the experiment begins. We fire the electrons not in a continuous stream, but one by one. We can even slow it down so that one electron hits the screen long before the next one is even fired. We watch as the first dot appears on the screen, then another, a third, a fourth. At first, the impacts seem random, scattered. But as thousands, then millions of these individual impacts accumulate, a ghostly and impossible pattern begins to emerge from the chaos. It is not the two-band pattern of particles. Inexplicably, it is the multi-band interference pattern of waves. Let the sheer impossibility of this sink in. We sent single, discrete particles one at a time, and they collectively created a pattern that could only be formed by a wave interfering with itself. How could this be? How could a single electron traveling alone know about the existence of both slits? It's as if each electron in its journey ceased to be a particle and became a wave of potential. It spread out and passed through both slits simultaneously, interfering with its own ghostly self before suddenly collapsing back to a single definite particle upon striking the screen. This concept gave birth to the idea of the wave function, one of the pillars of quantum theory. The wave function describes an unobserved particle not as a solid object, but as a cloud of probabilities. The electron isn't physically in multiple places at once, but its potential to be found is spread out like a wave. The densest parts of the wave represent the highest probability of finding the electron there. This idea, while mathematically sound, does little to comfort our intuition. We are left with a universe that, at its most fundamental level, seems to be governed not by certainty, but ethereal waves of possibility. The story, however, has another, even more profound twist. Faced with this impossible result, physicists naturally asked the obvious question: but which slit did it really go through? To answer this, they decided to watch. They modified the experiment by placing a sophisticated, non-invasive detector next to the slits, a tiny camera designed to register the presence of an electron as it passed by. The goal was simple: to catch each electron in the act, to force reality to show its hand and reveal the definitive path of the particle. The detector was switched on. The electrons were fired one by one. And the moment they were observed, the universe changed its behavior. The instant the detector registered which slit each electron went through, this one went left, that one went right, The interference pattern on the screen completely vanished. Gone were the multiple bands of wave-like behavior. In their place were just two simple bands, exactly the ones the classical marbles had produced. The very act of measuring, of gaining knowledge about the electron's path, forced the particle to abandon its wave-like multipath existence. It was as if the electron, upon realizing it was being watched, decided to behave itself and act like a respectable particle, picking a single slit and sticking to it. This is the observer effect, and it is perhaps the most unsettling discovery in the history of science. It reveals that the observer is not a passive spectator in the cosmic theater. The observer is a fundamental participant. The questions this raises are staggering. Does reality exist in a state of suspended, probabilistic animation until a conscious mind observes it? What constitutes an observation? Does it have to be a human, a machine, any interaction at all? This is the measurement problem, and it remains a deep, unresolved wound at the heart of quantum physics. This paradox ignited a historic debate between the titans of physics. Niels Bohr and the proponents of the Copenhagen interpretation argued that it's meaningless to ask what state a particle is in before you measure it. The unobserved reality is fundamentally indeterminate. The act of measurement creates the definite property. Albert Einstein famously detested this idea, retorting with his famous line, "God does not play dice with the universe." He believed there must be hidden variables, underlying properties we simply cannot yet see, that determine the outcome in advance. In the decades since, even more mind-bending interpretations have been proposed to explain this mystery. The many worlds interpretation proposed by Hugh Everett suggests that the electron really does go through both slits, but it does so in different, parallel universes. Every time a quantum measurement is made, the universe splits. In one universe, you measure the electron going through the left slit. In another, an identical U measures it going through the right. The interference pattern is, in this view, the result of these parallel realities brushing up against one another. Far from being a historical curiosity, this experiment's implications are the foundation of emerging technologies. Quantum computing, with its promise to revolutionize medicine and material science, relies on a computer's ability to hold information in a state of superposition, a complex version of an electron going through both slits at once, to perform calculations at unimaginable speeds. We began with a simple question: what happens when you fire a particle through two slits? We end with no simple answers, only a deeper appreciation for the profound mystery of existence. The double-slit experiment is a humbling lesson. It teaches us that the world is not as it seems, and that reality itself may be a fluid, participatory process that is shaped in some inexplicable way by the very act of our trying to understand it. It unveils a universe that is stranger, more magical, and infinitely more interesting than we ever dared to imagine. Has this journey into the quantum realm shattered your perception of reality? The universe is filled with even stranger truths waiting to be unveiled. If you found this exploration thought-provoking, like this article, share it with someone whose mind you want to expand, and comment below with your biggest question about the cosmos. Your curiosity fuels our next investigation.